All right, this is Chapter 8 homework for Physics 201. Have a force 1.3I plus 2.7J is applied at a point x equal 3, y equals 0. Find the torque about the origin. All right, so my force equals 1.3I plus 2.7J. That's in vector notation. I want to find the torque, and that's equal to R cross F. So I need to figure out what R is. The first one's pretty easy. It's about the origin. R is about the origin. It's from the origin, which is here, and x equals 3, y equals 0. So that's here. So my R for this one is 3I. All right, so let's go ahead and calculate that torque for part A. It's just going to be 3I crossed with 1.3I plus 2.7J. All right, now I cross I is equal to 0, so this is just going to be 3 times 2.7 times I cross J, which is equal to, what's that, 8.1 K. That's in Newton meters. And now for the next one, for part B, instead of being about the origin, it's about the point negative 1.3, 2.4. So negative 1.3, 2.4. So here, so my R vector is about that point down to there. And so I can find R. R is going to equal to 3 minus negative 1.3. That's in the I direction. Plus 0 minus 2.4. And that's in the J direction. So my torque then is going to equal 4.3I minus 2.4J crossed with my force, which is 1.3I. What was my force? 1.3I plus 2.7. J. All right. I cross I is equal to 0, J cross J, so all that. So if I do FOIL here, first, outer, inner, last, the first is I cross I, so that goes away. Outer is 4.3 times 2.7. And that's I cross J. Plus inner is negative 2.4 times 1.3. J cross I. Plus last is negative 2.4 times 2.7. That's J cross J. Oh, so that goes to 0. So that whole term goes away. So I'm left with 4.3 times 2.7. That's 12. I cross J is K. I always like to draw my coordinate system. This is I, J, K. You let your fingers go in the direction of I. They fold towards J. And then your thumb gives the direction, which is K. So it's going to be 12K. And then J cross I is going to be minus 3.1. That's 2.4 times 1.3 times J cross I, which is negative K. So I get 15K. Those are my answers. Calculate the net torque with magnitude and direction on this figure about an axis O, perpendicular to the page. So we're going about this axis. There are two torques. I'll call this one torque 1. I'll call this one torque 2. This force doesn't provide a torque about point O because it's applied at the axis of rotation. So I can I now want to ask myself, what is the direction of these torques? Well, torque 1 causes a counterclockwise torque, so it's positive, and torque 2 causes a clockwise torque, so it's negative. And then so for part A, the net torque is just equal to torque 1 minus torque 2. Torque 1 is going to be, remember, torque is equal to Fr sine of theta. All right, so my torque is equal to Fr sine theta. So torque 1 is going to be the force, which is 25 newtons, times the length of the moment arm, which is 2 meters for this one, times the sine of the angle. But I need to know this angle, which is 60 degrees. So sine of 60, that's the angle between the moment arm vector and the force vector. So my moment arm vector is, is in this direction, and so I need that angle. And then that gives me, and then I also have to include torque 2. It's negative, we've already said, 10 newtons, 4 meters, sine of 20. If I put those values in, I get my net torque to be 29 newton meters. It comes out positive, so I know that this has to be counterclockwise. Now, for part B, I need to ask myself, now instead of going around O, I'm now going around C. And so I'm going to have, I'll call this torque 1, and I'll call this torque 2. And then I need to reassess what are the directions of those torques. Torque 1 goes in this direction, so it's counterclockwise, so it's positive. Torque 2 goes in this direction, which is clockwise, so it's negative. All right, and then, so my net torque is going to be torque 1 minus torque 2. That's going to be 30 newtons times 2 meters. Times the sine of 45 minus torque 2, which is 10 newtons, 2 meters now, times the sine of 20. And then that gives me a net torque about that axis of 35 newton meters. It's positive, so it's counterclockwise. All right. I think that was it. Yes. All right, a cook holds a 2 kilogram carton of milk at arm's length, as in this figure. What force FB must be exerted? All right, let's just sort of redraw this. This is my axis of rotation, so I'm going to draw that there, and then I have a FB here. This angle is 60 degrees, and then I have the F weight of the milk. All right, the distance from here to here is 0.08 meters, and then the distance from here to here is 0.25 plus 0.08, which is what, 0.33 meters. And then it's a matter of balancing the torques. I know for this to be static that the sum of the torques equals 0. I'll call this torque 1. This will be torque 2. Torque 1 causes counterclockwise motion, so it's negative. Torque 2 is negative. Excuse me. Torque 1 causes counterclockwise motion, so it's positive. Torque 2 causes clockwise motion, so it's negative. And so I say torque 1 minus torque 2 equals 0. The whole thing about the clockwise, counterclockwise thing doesn't really matter here, because I'm just going to say torque 1 equals torque 2. I know that they're in opposite directions, so I know that they have to be equal and opposite. All right, torque 1 is going to be FW times 0.33 meters. Torque 2 is going to be FB times 0.08 meters. I'm going to go ahead and put in FW here. It's 2 kilograms times 9.8. And then if I solve for FB, in order to hold this, a couple pounds of milk, few pounds of milk, I have to exert almost 100 newtons, 93 newtons. That's because your bicep is attached very short distance from your elbow. All right, so it requires a big force to cause a torque to occur out at your hand. Solid sphere has a mass of 3,000 kilograms and a radius of 4 meters. Sphere is able to rotate about its center point and is initially at rest. The sphere is turned by a wheel that exerts a force, 3I minus 4K on the sphere. these coordinates, 1, 3, 0. What is the torque acting on the sphere? All right, part A is pretty simple. Torque is equal to R cross F. My R is going to be 1I plus 3J. That just comes from these coordinates because it's acting about the about its center point, which we call the origin, 1I plus 3J. And then the the force is 3I minus 4K. Now I need to do this. Let's see, the first 1 times 3, I cross I, that goes to 0. Outer is 1 times negative 4. That's negative 4I cross K. Inner is 3 times 3, that's 9. J cross I. And then last is 3 times negative 4, that's negative 12. J cross K. All right, I like to do my coordinates over here, I, J, and K. All right, I cross K. I let my fingers go in the direction of I. They fold towards K. That's negative J. So I have 4J. J cross I. Fingers in the direction of I. They fold, fingers in the direction of J. They fold towards I. And so my thumb points in the negative K direction, minus 9K. And then J cross K. Fingers in the direction of J. They fold towards K. That's the positive I direction. So I have 4J minus 9K minus 12I. That's my torque. That's part A. How long does it take for the sphere to reach a speed of 20 revolutions per second? All right, so I want to know omega is 20 revolutions per second. I'm going to go ahead and convert this to radians per second. 1 revolution is 2 pi radians. So 20 times 2 pi. Let's see, I did this incorrectly in my notes, so calculate this. That's 40 times pi. Get 130. 130 radians per second. I know that's initially at rest, so omega naught is equal to 0. I want to know the time. And so this should start to look like one of your kinematics equations. Omega equals omega naught plus alpha t. In order to solve for t, I need to find alpha, and omega naught goes away. So t would equal omega over alpha. But I don't have alpha, so I need to find that. However, I know that there's a torque applied to this, and I know that torque by Newton's second law is equal to I times alpha. So alpha is equal to the torque over the moment of inertia. This gives us our angular acceleration. All right, so I have this. It's my torque is equal to 4J minus 9K minus 12I. All over my moment of inertia. Now, my moment of inertia, I'll do this sort of up here, for a sphere, which is what I have, is equal to, if I look back on my table, it's 2/5 mr squared. That's equal to 2/5 of m, which was 3,000 kilograms, times r squared, which is 4 meters squared, and that gives me 19,200 kilogram meters squared. So this is all over 19,200. All right, and that gives me, in vector notation, an alpha of 6.25 times 10 to the minus 4. That's in the I direction, okay? So that's actually negative 6.25 times 10 to the minus 4 in the I direction, plus 2.08 times 10 to the minus 4. That's in the j direction, minus 9 over 19, 200, 4.69 times 10 to the minus 4. All right, so that gives me my alpha in vector notation. Now, if I want to know the magnitude of alpha, use the Pythagorean theorem, but in 3 dimensions. So that's going to be the square root of the x component of the vector squared plus the y component of the vector squared plus the z component of the vector squared. So I'm going to take the square root of this number squared plus this number squared plus this number squared, and that gives me a value of 8.1 times 10 to the minus 4 radians per second squared. So that is the magnitude of my alpha, and I'm going to use that over here to find t. So t is going to equal to 130 radians per second divided by 8.1 times 10 to the minus 4 radians per second squared. So my time then is pretty big. It's going to be 160,000 seconds. 160,000 seconds. That's to get this. This is a big old sphere, and it's not a very big force that you're applying to it. So it's going to take quite a while to get up to the speed of 20 revolutions per second, which is a pretty fast speed. All right, now I want to know how many revolutions does the sphere rotate before reaching that speed. All right, so let's see. I'm running out of space here, but c, just want to know theta omega naught is equal to 0, so this is just 1/2 alpha t squared. That's 1/2 of my alpha, which is 8.1 10 to the minus 4 times 160,000 squared. Get 1 times 10 to the 7th. Is that right? That's in radians. And then I need to divide by 2 pi. And I get 1.6 million. 1.6 times 10 to the 6 revolutions. That's a lot. Although it takes a really long time to get going. All right? All right, for number 5, I have 4 objects that are held in position at the corners of a rectangle by light rods as shown in this figure. Let's see, there's a little mistake here. These numbers are just switched. So this should say 4 meters, and this should say 6 meters. All right, in the first part, I just want to know the moment of inertia about the x-axis. So that's, excuse me. That is the moment of inertia as it rotates about this axis. That means that my length of my moment arm is going to be half of 6, which is 3 meters. And likewise for these masses, it's also going to be 3 meters. That's about the x-axis. So I is the sum of mr squared. So it's going to be 3 kilograms times r squared, which is 3 meters, plus 2 kilograms times r squared, which is 3 meters, plus the masses at the bottom, 2 and 4 kilograms. You just add up mr squared for each individual particle. And notice that they all have the same r, so I could just as well write it as just factor out 3 squared. Alright, so that's 3 plus 2 is 5, 7, 11 times 9, that's 99 kilogram meter squared. Actually, it's 99.0 kilogram meter squared. And then for part B, I want to know it about the y-axis. So that is, I'm rotating about this axis. So now my distance here is going to be half of 4, that's 2 meters. And so I can write it. I'm just going to go ahead and factor it out. That's going to be 3, all the masses, plus 2, plus 2, plus 4. That's kilograms times my distance, which is 2 meters squared. That's 11 times 4 is 44.0. Alright, and then for part C, let's see, I want to know if it rotates about this axis. That means that my moment arm is going to be this distance. I can draw a triangle here. I have a 2 meter, 3 meter, so I can find the length of that hypotenuse is square root of 2 squared plus 3 squared, that's 4, plus 9 is 13, so the square root of 13 is 3.61. So this is 3.61 meters. Let's do the same thing, but now with a different moment arm. So the sum of all those masses is 11 kilograms times 3.61 meters. That's squared. And then I get 143. So notice how the moment of inertia is a lot bigger when it's rotating about that axis. It's also bigger when it rotates about the x-axis. That's because r is bigger for those masses. So you can have the same masses but very different moments of inertia dependent upon the axes of rotation. Right, a 10 kilogram cylinder rolls without slipping on a rough surface. Center of gravity has a speed of 10 meters per second. I want to know its translational kinetic energy. That's just 1/2 mv squared. I have my mass as 10 kilograms. It's traveling at 10 meters per second. It's half of 5 times 100, that's 500 joules. But then I also want to know what is its rotational energy. Because it has energy just from traveling forward, and then also energy because it's rotating. So that's 1/2 I omega squared. I'm going to go and make some substitutions here. I for a cylinder is 1/2 mr squared. And then omega, if you remember, V is equal to omega times R. So omega is equal to V over R. So I'm going to put that in for omega because I don't know omega. So that's V over R squared, V over R quantity squared. Fortunately, these R's cancel out. And I get it's equal to 1/4 mv squared. And so that's equal to 250 joules. And then the total energy, it has energy just from traveling forward, plus energy from rotating, is 500 plus 250 is 750 joules. Okay, horizontal 800 Newton merry-go-round, a radius 1.5 meters, started from rest by a constant horizontal force, 50 newtons applied tangentially to the merry-go-round. We'll know the kinetic energy of the merry-go-round after 3 seconds. All right, kinetic energy is 1/2 I omega squared. So I need to know what is I. I can find that over here. I for a disk is 1/2 mr squared. All right, I need to find my mass. I'm going to do it up here. Mass is equal to the force weight over gravity. That's 800 over 9.8. So it's about 80 kilograms. So my moment of inertia is 1/2 of 80 kilograms times my radius squared of 1.5 meters. And that gives me a moment of inertia of 90 kilogram meters squared. Okay, so now I know I. That's one step. Now I need to find omega. I know that omega is equal to omega naught plus alpha t. All right. I know my time is 3 seconds. I know my omega naught. It says that it is initially at rest, so that tells me that omega naught is 0. All right, but I don't know alpha, so I need to find alpha. So I'm going to go off here to the side and find alpha. I know that torque is equal to I times alpha. That's from Newton's second law. So alpha is just the torque over the moment of inertia. That's going to be force times the length of the moment arm over I. The force is 50 newtons. See, I have this disc, and I'm applying a force of 50 newtons here at a moment arm of 1.5 meters. 50 newtons tangentially at the edge of the merry-go-round. So it's 50 times 1.5 over my I, which is 90. And then that gives me an angular acceleration of 0.8 radians per second squared. So now I'm ready to find omega. Omega is equal to alpha times t. That's 0.8 times 3 seconds. All right, and now that I know that, I can come back over here and find my kinetic energy. 1/2 of I we said was 90. And omega is 2.4. And so that gives me a kinetic energy of 260 joules. That's the answer. All right, system of small objects is rotating at an angular speed of 2 revolutions per second. The objects are connected by light flexible spokes that can be lengthened or shortened. What's the new angular speed if the spokes are shortened to 0.5 meters? And so we get a similar thing when we have the collapse of star-forming regions, because you have these very slowly rotating yet very massive and very large objects, and then they contract down to smaller sizes, and the speed is going to be really, really large when you contract. It's like the figure skater pulling her arms in. She goes a lot faster when she pulls her arms in. So look, we can find this from the moment conservation of angular momentum. That is that L naught is equal to L final. All right, here we have 4 different particles, or rather, so then we say I naught omega naught equals I final omega final. Remember, we're sort of comparing this to what we used to do with linear momentum, where now we're replacing our mass with our moment of inertia and our velocity with our angular velocity. All right, I naught is going to be the sum of mr squared, where r is equal to 1 meter. That's our initial r, times omega naught. And then I final is going to be the sum of mr final squared, where r final is going to equal 0.5 meters, because it says that the balls all come in, times omega final. So there are 4 masses, all of mass m. So I'm going to have 4m times 1 meter squared times omega naught. That was given, it was 2 revolutions per second. And that's going to equal 4m, 4 because there are 4 masses of mass m, times 0.5 meters squared, times omega final. Now the masses cancel out. It doesn't really matter what the masses are. The 4's cancel out too. And I can solve for omega final. It's going to be 1 squared times 2 over a quarter. What's that? 8 revolutions per second. So it's going quite a bit faster, 4 times as fast when it contracts to half its original size. Potter's wheel with rotational inertia, 6.4 kilogram meters squared, spinning freely at 19 revolutions per minute. Potter drops 2.7 kilogram lump of clay where it sticks at a distance 40 centimeters from the rotation axis. So I have a Potter's wheel. It's rotating Let's say it's rotating in this direction. It doesn't say, but let's say that it is. So that's my omega. And then, we'll call this omega naught. And then I drop a big lump of clay right on the edge. And I want to know now, what is omega final? All right? So, I just say that L naught equals L final. That is I naught omega naught equals I final omega final. I naught was given, that's 6.40. And then I also know what my initial speed is. It's 19 revolutions per minute. I'm just going to keep it in RPMs. You can do that with the conservation of momentum. The units all cancel out. I final. I'm adding this lump of clay. So my I final is going to be 6.4. That's just the moment of inertia of the wheel plus mr squared for the lump of clay. So it's going to be 2.70. That's the mass times r, which is 0.460 meters. That's mr squared. So the moment of inertia over here is equal to I of the wheel plus I of the clay. And you just treat the clay as a discrete particle. So its moment of inertia is just the mass times the moment arm squared. This is all times omega final. If I solve that for omega final, I get 17.4 revolutions per minute. So notice that it goes slower. It was going 19 revolutions per minute, and then you drop this new mass onto it, and it slows down because of conservation of momentum. This is a technique that you can use in mechanical systems in order to slow down things that are rotating. Instead of braking the system, not braking like braking it, but like braking like applying brakes, you can increase the mass of the system, and that will cause it to slow down as well. Okay, uniform spherical cloud of interstellar gas has a mass and a radius is given. It's rotating over that period. If the cloud collapses to form a star, 7 times 10 to the 8 meters in radius, what will be the star's rotation period? So again, L naught is equal to LF, I naught omega naught equals I final omega final. I naught, or I for a sphere, a solid sphere, is 2/5 mr squared. I'm going to put that in over here for I naught. 2/5 m is 2 times 10 to the 30th. And then my radius is 1 times 10 to the 13th. So I have this really big, really massive cloud of stuff. And it's rotating 1 revolution every 1.4 million years. So my omega is going to be 1 revolution every 1.4 times 10 to the 6 years. Okay? And now my new moment of inertia, because all of that mass conceivably goes down into a star of 7 times 10 to the 8th meters in radius. The fact of the matter is, though, that it doesn't really all go into the star, that you lose some of the mass. It goes out into the surrounding medium, outflows and what have you. But for the most part, we can say that all the mass goes into the star. And then I want to know, what is the new period? 1 revolution over 1 period. I'm going to be solving for t. If I solve this for t, I find that t is equal to 2.5 days. That might not mean much to you, but that's the rotation period of the star. It's really fast, 2.5 days. For example, the sun, for the sun, t is equal to 25 days. So we're talking about an order of magnitude, and this an order of magnitude off by a factor of 10. And that's sort of a major problem in star formation. There are a variety of ways to fix that problem, but this is just a simple calculation. We see what should be the rotation of the star, and then when we observe the rotation periods of stars, they're actually quite a bit longer than what we should expect. All right, one more. Disk has a mass of 10 kilograms and a radius of 2 meters, spinning at a rate of 3 revolutions per second. So this is my disk. mass of 10 kilograms. I can go and calculate the moment of inertia for a disk. It's mr squared. That's 1/2 of 10 times the radius, 2 squared. That's 20 kilogram meter squared. Now let's say that it's rotating in the counterclockwise direction. That's 3 revolutions per second equals omega for that disk. It doesn't say. I'm just going to say it's in the clockwise clockwise direction. So that's negative 3 revolutions per second actually. And then I have a bar over here, and it's also spinning, but in the opposite direction. It's rotating about this axis, and it's spinning at a rate of 2 revolutions per second. Now I'm going to solve for its moment of inertia. That's going to be 1/12 mb squared. 1/12 of 3 times 4 squared. That's 4 kilogram meter squared. Now, when I bring these two together, they have a certain amount of momentum. They have a certain angular momentum, L naught, and that has to equal the final angular momentum. So what I'm going to do is I'm going to take these two guys, I'm going to put them together and have them rotate about that axis, and I want to figure out what is the new rotation rate. So now, instead of just having one particle that's changing, I have two things that are changing. We did an example like this in class. This is like an inelastic collision, a perfectly inelastic collision. You remember before when we talked about linear momentum, we had two objects that were moving, and then they come together, and they have the same velocity. All right, it's called a perfectly inelastic collision. This is a similar thing, except they're rotating. All right, so I just add up the initial momentum. That's going to be 20 I omega naught for the disk plus I omega naught for the bar, and then it's going to equal I final omega final. All right, so I have 20 times negative 3 plus 4 times 2 is equal to 20 plus 4, that's the combined moment of inertia, times omega final. And then if I solve this for omega final, I get negative 2.2 revolutions per second. And since it's negative, it's in the clockwise direction. So this thing is going to travel in this direction at 2.2 revolutions per second. Said in mechanical systems, this is commonly happens where you have these two rotating things that come together and they begin to move at the same speed. Gears, for example, all right, but also sometimes you get them on the same axis where they're moving along the same axis like this.